Welcome back. Let's define local max and local mean values of a function of two variables. Um, so let's let z be f of xy, and it is a function that is defined on an open subset U of the two space, and let's say that P is a point in U. Now we say that f has a local maximum at the point P if there exists an open disk or a ball centered at P such that f of xy such that f of P is greater than f of xy for any xy in B. On the other hand, we can define the local minimum in a similar way. So f of xy has a local minimum at the point P if there exists an open disk or ball B centered at P such that f of P is less than f of xy for any xy in B. So here is the graph of a function of two variables. So notice that at the red dots we have local maximum values, and at the blue dots we have the local minimum values of the function f. Now at this point right here we have the absolute maximum of the function, and at this point here we have the absolute minimum of the function. So absolute maximum is the maximum of the function on the entire domain of the function. So why is this a local maximum, or this one is the local maximum? Well, we can take a very small piece of the graph centered at this point, where this point is the highest point on that piece. Similarly here, you see this point is the highest point on a small piece centered at that point. This is the local minimum because this point is the lowest point on a small piece centered at that point. So these are the points where the function f has local minimum values. So one thing you can notice is that if the function is differentiable at a point P, then at that point the tangent plane, so if I have a local max, and if the gradient is defined there, then if f is differentiable there, then you can see that the tangent plane is horizontal there. And so these points that we have here, these are called critical points. So let me formally define what a critical point is. We say that the function f, let's say f is a function defined on an open subset U of the two space. P is a point in U. We say that P is a critical point of f if either the gradient of f at P is 0, or if the gradient of f doesn't exist at P. So remember, I am defining the gradient to be the first derivative of the function. So I can say that P is a critical point of f if the first derivative of f is 0, or the first derivative of f doesn't exist at the point P. Now the gradient is 0 simply means that the partials of f at P are equal to 0. So basically, critical points are points where the gradient is undefined, or the gradient is zero. In other words, where the partials are zero. Here's a theorem. It says that if f has a local max or a local mean, so extrema means it's a local max or a local mean. So if f has a local max or a local mean at the point P, and if f is differentiable at the point P, then the gradient of f at P must be zero. In other words, the partials at P must be zero, and which means that P is a critical point of f. So basically what we are saying is that if f has a local max or a mean at the point P, and if f is differentiable at P, then P must be a critical point of f. Let's find the critical points of this function. So here I have a function of xy, and we want to find the critical points of f. To do so, the first thing I need to do is find the partials. So what's the partial derivative of f with respect to x? Well, that's going to be 2x minus 2. And what's the partial with respect to y? Well, that's going to be 2y minus 6. So these are the partials, and to find the critical points, I have to find points where these partials are simultaneously zero. So that means I have to solve the system of equations where the first equation is 2x minus 2 is 0, and the second one is 2y minus 6 is 0. The first equation here tells me that x is 1. The second equation here tells me that x is 3. So we see that there is only one point, 1, 3, where both of the partials are equal to 0. So this is the only critical point of this function. Obviously, these partial derivatives are defined at any point xy. Again, the same question, we want to find the critical points of the function x to the 4 plus y to the 4 minus 4xy plus 1. Well, we find the partials, so the partial derivative with respect to x would be 4x cubed minus 4y. The partial with respect to y would be 4y cubed minus 4x. So these are the partials. So we set the partials to 0, and we need to solve this system of equations. So this is the system of equations that we want to solve for x and y. Now, the first equation, we can cancel out the 4 by dividing both sides by 4. So then I get x cubed minus y is 0, and then I can rewrite that as y is equal to x cubed. So here, this first equation can be expressed as y is equal to x cubed. The second equation, we can express that if I divide by 4, I can write that as y cubed minus x is equal to 0. Okay, so now what I'm going to do is I'm going to substitute x cubed. So since y is x cubed, I'm going to substitute that for y in the second equation. So if I replace y by x cubed, then I get x cubed cubed minus x is 0. So that's giving me x to the 9 minus x is 0. Now x to the 9 minus x, if I factor out x here, then I get x times x to the 8 minus 1. So from here I get that either x is 0, or x to the 8 minus 1 is 0, or x to the 8 is 1. And so if x to the 8 is 1, then x is either 1 or minus 1. So these are the x values that I get. Now for each of these x values, I have to compute the y value. So when x is 0, y is 0, so I get the point 0, 0. When x is negative 1, y would be negative 1, so I get the point negative 1, negative 1. And when x is 1, y is 1, so I get the point 1, 1. And these are the critical points of this function because the partials are defined at any point, so there aren't any points where the gradient is undefined. So when we have a critical point at a point, when we have a critical point at P, it means that the gradient of f at P is 0, 0. That is, the partials vanish at P, right? Now, at a critical point, it turns out that at a critical point where the gradient is vanishing, the tangent plane there would be horizontal. That is, the tangent plane. So if I'm assuming that gradient of f at P is 0, 0, then at the point P, f of P, the tangent plane would be parallel to the xy plane. Because recall that from our discussion on tangent planes, that at this point the normal vector is given by fx, fy, and -1, and because fx, fy are both 0, then you get the vector 0, 0, -1, which is a vector that is parallel to the z-axis. So that tells you that the tangent plane here would be parallel to the xy plane. So the tangent plane at P would be horizontal if the gradient at P is the vector 0, 0. Now, so in each of these three pictures, you can see that the tangent plane is horizontal at the point P, f of P. Now, one of these three cases can occur. So in the first case, yes, the gradient, we have a critical point at P where the gradient vanishes and the tangent plane is horizontal, and at that point we have a local max, where we have a local max at this point. In the second case that can happen is that again, the tangent plane is horizontal, P is the critical point, but we have a local minimum here. And the third case that can happen is that at the point P, f of P, we have a saddle. This is a saddle point, which means that, notice that the gradient is still vanishing at this point. The tangent plane is still horizontal at this point. However, this is neither a local max nor a local mean, because if you look at the points on this curve, then this is the lowest point. But if you look at the points on the dotted line on the graph of f, then you have that this is the highest point. So this is neither local max or local mean. So the point I want to make here is that when we have a critical point P, at that point, either we have a local max or a local mean or a saddle point. Okay, so I'll stop here, and in the next video we will be looking at the second derivative test, where it is a test to check whether whether at a critical point we have a local max or a local mean.